Cool.
Nice.
Thank you, thank you. I did not choose the voice. Um, okay, so welcome everyone. So this week's like deep learning theory seminar. So this week we have like the great honor of having Chiara Amorino with us. So Chiara honestly is an expert in various different aspects of statistics and stochastic processes and differential privacy, which is what we should be talking to us today about. So just a quick word about Chiara. So met Chiara this summer. Um, and yeah, well, at a math finance conference somehow. Yeah, so Chiara has done her postdoc in the University of Luxembourg with Mark Podolsky. I got better at saying his name recently. And before her PhD at University Paris-Saclay with Arnaud Gloter, which is like his co-author of this work. Um, right, and right now, Chiara has a great position at the University of Pompeu Fabra, like 4 minutes from the beach, so it could not be better in Barcelona. But anyways, so today she'll be speaking to us a very interesting result that has just recently come in Annals of Statistics. So Minimax optimal convergence rates under componentwise local DP. So very interesting. So to you, Chiara.
Thank you very much. Oh, what a nice introduction. I like it very much. Amazing, especially the part about Barcelona. Yeah, thanks. This is well, as you said already, this is the paper this talk is based on. So let's start directly by introducing what all this is about. First of all, okay, I'm a statistician, and nowadays we have a lot of data. We have more and more data, everything is beautiful, we are super happy about it, but a lot of this data actually are sensitive, and so we should be able to ensure some amount of privacy on it, right? But we have to be careful about it because, of course, if we can see the data and we can exploit all the information about the data, our statistical guarantees will be better. On the other side, if we need to ensure some amount of privacy on the data, this is very heuristic, very natural. If we give some privacy to the data, it means that we are hiding something, and as we hide that something, well, actually we are losing a bit of statistical utility, and so our statistical guarantees in general will be a bit worse. What we want to do now is to try to understand how worse and how to find a nice trade-off between this statistical utility and the privacy guarantees. But so far, I'm just talking about privacy in a very general way. So there are a lot of ways of anonymizing data. And well, a lot of them didn't work. There is a quite famous event done by Netflix in which it was clear that classical anonymization procedure didn't work. And the nice thing was that the work arrived in 2006, introduced what is called central differential privacy or global differential privacy. But here in this work, we are going to focus on local differential privacy. What's the difference? Well, when you have central privacy, it means that you have a guarantee, a trustee who can see all the data, okay? He privatized the data, and then you just get later on some privatized statistics. While local differential privacy, it's a bit different in the sense that the data are obfuscated locally, okay, by the individuals directly, and then the statistician gets directly the data that are obfuscated. And then, starting from this like public version of the data, we have to do some statistics. Okay, of course, later on we are going to formalize everything. I'm going to give you all the math because we like math. But so far, let's just give an heuristic idea of what's happening here. And the idea is that, well, we want to focus on local differential privacy, so we get these data that are already obfuscated somehow, and starting from this data, we want to do statistics. But here, in the talk, in the title, I talked about component-wise local differential privacy. What does it mean? Well, basically, I want to consider a multivariate setting, and I want to see how giving different level of privacy to different components can change all this game. But first of all, why do I want to do so? Well, it's nice if you think about the data as if they were different people, individuals, okay? And each individual is in dimension d, which d that can be large. And each component is just a characteristic of this person, right? And nowadays, again, we are in the time of the big data. So it means that for each person, we can have a lot of data. For each person, we can see, I don't know, how much he's spending in buying bags, buying shoes, doing different things in, I don't know, electricity, different things, okay? But we have to be careful because of two things. First of all, these things may be correlated. And second things, well, maybe these things deserve different level of privacy. That's the whole idea. I'm going to explain it way more in detail. But the point is really that if we consider some multivariate setting, then for each component, it may have sense to consider different level of privacy. So not only we're going to consider different level of privacy, but we're going to consider really different privacy mechanism for each component. We're going to formalize everything, don't worry about it. But I wanted just to give an introduction about it. So why do we want to consider component-wise local differential privacy? Let's give a bit more of details. And as I was saying, for each vector, we can consider to have like n vector as if they were n people. And for each people, we have like this D, different components, and each component is a different things. As I was saying before, it may have sense to say that, I don't know, the first one is the salary that a person is getting. So it's highly sensitive, right? Maybe, I mean, you don't want to say how much you're getting. So that information is highly sensitive and requires a high level of privacy, while some others may be less sensitive. Like maybe it's okay for you to tell me how many pair of shoes you bought last month. I see you checking. Well, the point
One.
is that once, good. Well, maybe I can infer something. If I see that, for example, you buy one pair of shoes per day, well, I can infer that your salary may be higher than a certain amount, right? And well, there are a lot of examples like that. So we are going to give a certain level alpha j of privacy to each component, for j going from 1 to d. And then we are going to say, yes, maybe we collect data and we want to give different level of privacy because uh, things are maybe more or less sensitive, but we have to be careful about the effective privacy. So the effective privacy is really the fact that even though I'm giving a less amount of privacy about the second component that tells you how many times you bought bags, still it helps me understanding something about how is your salary. Same things about the example that I wrote here. If X1 represents data related to sport practice, we have to consider the fact that like local differential privacy is used in practice. So for example, Apple and Google used it. And there are a lot of applications on the phone keeping track on how much sport you do and which kind of sport you do, like running application, this kind of stuff. So actually, you are giving information about like how much sport you are doing, and I can infer something about your healthness from there. Okay, so if I really want to cover X2, I have to be careful because I cannot give too much information about X1. Otherwise, I will recover information about X2 as well. And this is called effective privacy. We are going to see that in detail later on. The second example is a bit different, and it's the fact that maybe me as a statistician, I'm getting data from two different companies. For example, let's say that X1 is how much I'm spending in health insurance, and the second one is like is given by the tax office because it's saying how much I'm spending in taxes. And these two different companies may have two different privacy policies, right? So me as a statistician, I can get data directly from them, and they give me the data with two different type of alpha. And I have to be able to say something about the data, even though the alpha is not the same. Okay, so the first example is like a choice. The fact that maybe you want to have different level of alpha. The second one is more like, yeah, it's not like we have much choice. We get different data with different level of privacy, and we want to be able to say something. Dot. Okay? So, it starts the moment where I have to move you around. Here, you're going to stay here. So, the goal is to understand this trade-off between the privacy protection and the statistical utility, as I was saying at the beginning, but being careful about the fact that, well, this trade-off is a bit more complicated if we have to consider not only one alpha parameter, who is quantifying how much privacy I'm giving to the whole vector, but I have the different parameters that can play together with who are telling me how much privacy I'm giving to each component. Okay, how can we talk about privacy? Like, what is this component-wise local differential privacy? So now let's do everything in a formal way. We start by giving like proper definition. And I later on actually compare also this definition with the classical local differential privacy, also because I'm not sure how familiar you are with the local differential privacy. But basically, what we want to do in both cases, okay, when you have local differential privacy or component-wise local differential privacy, is to say, I'm starting with a certain sample, x1, xn, that in this case, yes, yes, come, don't worry. So we have a certain sample, okay, x1, xn, and this sample are the actual data coming from the individuals that may be sensitive, that should be privatized. Okay? So we take this X and zoom, we transform them into some Z, which are now the public version of the original X. Okay? And here in CLDP, what happens is that starting from each component of X, I'll get a different Z. This QJ, I'm going to call them privacy mechanism or Markov channel or Markov mechanism. It's always going to be the same, okay? It's just this big Q, okay? So the important thing about CLDP is that from each component of each sample, I'm going to get a different component of the new sample Z. It means that the, the kernel Q is different for each component. But here, I don't know if you see the fact that the kernel Q does not depend on I. This is the non-interactive case. It means that the notation is the following. When I talk about something that it's down, this I, it means that I'm talking about which individuals of the sample it is, while the J is explaining to us which component I am considering. So what I'm saying is that the important thing about CLDP is that the kernel mechanism is different for each component. Why that? Well, because I'm saying that I want to give different amount of privacy to the different components, right? And so, for example, to the first component that was the salary, I'm going to give a certain level of privacy, so I'm going to use a certain mechanism. For the second component, I'll use another one, and so on. So this is really important about CLDP. Then the difference between non-interactive case and sequential interactive privacy mechanism is the same that one would have for the local differential privacy, meaning for the non-interactive case, you start with some, if for example you start with some IID random variables, even after the Z are IID random variables. Okay? While with the sequential interactive mechanism, it's a bit different because you start with the first person. I have your data, Anastasis, and I start with your data and I create a Z, okay, a public version of your data. Then I take the second person, the one that joined late, and in order to make a public version of his data, I will use the private version of his data, but also the public one that I've already done using your data. Okay, and so on. So each time that I want to do a new data, I'm also using all the public data Z that I have already. Now, on one side, this may seem a bit more complicated because even if you start with IID's data, the X were IID's data, the Z are not. The Z are not IID because you are using them again. But on the other side, you are keeping more information because it means that when I construct Z2, I'm using again data from Z1, and so actually I'm trying to improve my statistical utility using the same data over and over again. So it's like I'm trying to get something more from your data, not only when I construct Z1, but even when I construct Z2 and so on. Okay, this is the idea. And the important thing is that we have to quantify privacy because so far everything is beautiful. We are saying that from X that are private, we get a set Z that is public, cool, through a privacy mechanism. But if we cannot say how much information we are losing, that's not so useful.
All
So,
right, just one question. So we're not assuming that the D components are independent, right? They come from different distributions, but they can be dependent on each other.
yes, exactly, they can be dependent. What are independent are
Is
the
the
sample.
individual samples. Okay,
Yeah,
makes sense.
exactly. That's a very good point. Yes, the component may be dependent. That's the interesting part, right?
Yeah, yeah. Okay, cool.
Indeed. Good. So yes, we go on then quantifying how much privacy we are giving to each component. And well, this is done in a way that is very much similar to the one that is used in the classical LDP that I'm going to write later on. But the idea is really to try to understand how much Z see of a difference in the original data set. So here I'm seeing what happens if the original component J of the sample I was equal to X or was equal to X prime. And A is inside the sigma algebra of Zj, meaning, I mean, it's a quite complicated way of saying just that the parameter alpha j, can be between 0 and infinity. And when alpha is equal to 0, it means that here we have perfect privacy and we do not see any difference between between the original sample being equal to x or another x prime. Nothing changed. We don't see anything. While for alpha j going to infinity, this privacy constraint is less and less strong until at a certain point it's like you are recovering all the information and you can really say if the original variable was x or x prime. And we have the very same definition also in the case where instead of considering the non-interactive case, we have the interactive one. Okay, and just to give, and here the point is really the same because Z actually is something that we are using, but it doesn't change in the numerator or in the denominator. Again, the only one thing that I want to understand is how much of a difference I can see if the original private variable changes. Okay, and this is really parameterized by alpha j. So alpha j is telling us how much privacy I'm giving to the component j. That means that the privacy parameter is not going to be just a real number, but this is going to be in RD because I have the privacy given to the first component and so on until the component D. Okay. Are there any questions?
Yeah, maybe one question
Yeah,
I
yeah,
asked.
sure,
So
cool.
then it doesn't, this alpha J
Mhm.
doesn't really, right? Like, because you're using like the public data from everyone. So the alpha J is going to be the same for everyone. So the alpha vector is going to be the same for everyone. You're just using the public information for better utility, right? Okay, okay, just
Exactly.
like, yeah, it's pretty interesting. I just want to make sure I understand the setup correct.
Exactly. Yeah, yeah, no, that's great. I like it. Also because we are online, so I don't see your face. That's nice that at least I don't know, we talk. So
That's
yeah,
true.
please ask me again everything you want. But yes, that's exactly the point because all the individuals, for me, they are IID, so they really have the same they play the same role. So alpha is the same for all of them. What changes is just how much privacy I'm giving to each component, but same for everyone. And also because, of course, I'm taking like a data set where for each person, I have the same information, right? They are really IID. So it means that the first component is the salary for all of them, right? And so on.
Okay, makes sense.
Thank you. So, well, just let us compare to what happens in the LDP case, because the component-wise local differential privacy is what we have introduced. Before there was the LDP, local differential privacy, that actually applies also to a multivariate case. So you can consider a vector X. But what happens is that you take the whole vector, okay, X, you put it inside this privacy mechanism and you get a new vector Z, okay? So you have just one privacy mechanism for all the component. Of course, then you can also like generalize it in the sequential interactive, where again, you take one X and you create Z, then you take the new data from you and then you take what you have already created by Z and so on. But again, the important thing is that in all the cases, you are just taking the old vector and you're applying the privacy mechanism to the old vector, getting a new one. And that's the reason why when you then want to quantify how much privacy you are giving, well, you are giving a certain amount of privacy, it is just alpha, because you have one privacy mechanism, and so moving from the old vector X to the old vector X prime, how much can I see of a difference just looking at Z? Well, certain alpha. That again, exactly as before, can be between 0 and infinity. If alpha is equal to 0, it means that I cannot see any difference. It's the case of perfect privacy. While for alpha going into infinity, it means that this privacy constraint is weaker and weaker. And now we actually want to understand, we want to go back, like this is just all the formalism needed to introduce the component-wise local differential privacy. But now we want to face the problem of the trade-off between statistical utility and privacy constraint. So we want to understand, in the case where we access some data and we want to privatize them, okay, how much privacy we should give to the system in order to recover some results that are still good? Or how can I choose a privacy mechanism such that the statistical utility is as good as possible? In order to answer to this question, the first thing is to say, okay, well, actually, if we have just some data without any type of privacy constraint, okay, and we want just to do some statistics, at the beginning we could ask like a similar question. Instead of asking what's the best privacy mechanism, we could just ask what's the best estimator we can introduce in order to get the result as good as possible, right? And there are some different way of defining what is an optimal estimator, the best estimator, no? What I'm going to focus on is an estimator that is optimal in a minimax way, in a minimax sense. Meaning, let's say that I have some IID data, x1, xn, and I want to estimate some parameter theta, okay? I want to create an estimator theta hat that hopefully is consistent, and I want to understand, first of all, how fast this is going to converge to the actual parameter theta for n going to infinity. So after that, we would like to start to study the inf over all the possible estimator, and we would like to say, hey, actually, this is the best we can do, okay? It's not possible to propose another estimator that converges to the actual parameter faster than the convergence rate we found in this particular case, okay? And this was like the classical Minimax framework without any type of privacy constraint. Then we want to introduce the same, taking into account that we have CLDP. How? Well, now we have some data that are no longer the X, but the actual data that we can see are only the Z, right? Are the public version. And well, what we can say is that finally, an estimator is just a measurable function of the data. And this data Z are just like a transformation of the original X. So it's like we are considering a composite function. And then the question is, if I consider all the possible privacy mechanism, which one is the best? Well, what I can do is to propose an estimator that is based on the Z and propose a privacy mechanism that allow us to move from X to Z so that I have this composite function. And then I want to look for the best, but not only the best estimator based on the Z, also to the best function that we had before, the function that allowed us to move from X to Z, so the privacy mechanism. That's the reason why I have this double inf over here. I have the infer over all the possible estimator, that is this function that I'm going to use exactly as I did before to understand how good my estimator is. But also here, as I'm writing the Z1, Z, and D, I'm also saying that I have another function that are actually the privacy mechanism, transforming the X into Z. So the inf is not only over all the possible estimator, but it's also over all the possible privacy mechanism. That means that if I fix a certain level alpha of privacy that I would like to have, meaning I fix alpha 1, alpha d, I'm fixing all the privacy level that I want to give to the different component, then I can say, what's the best privacy mechanism satisfying this level alpha of privacy what's the best privacy mechanism among all of them satisfying this level alpha of privacy? That is exactly the same you would do with the estimator. You propose an estimator, and then you try to understand if it's optimal in a Minimax way. Among all the possible estimator, is it possible to find another one for which the convergence rate is faster? Now the convergence rate will depend also on alpha, but I'm asking the same. I propose an estimator and a privacy mechanism, and then I ask, is there another privacy mechanism for which this consistency is faster? That's the question. And actually, to answer, answering is a bit tricky because in order to do that, we need to be able to move again to the X, meaning the estimator is based on the public version of the data, is based on the Z, but I need to be able to know that if the original law of true data set were close, also the law of the true data set after this privacy mechanism are still closed. And this is really given just by the fact that I don't know how familiar you are with using lower bound, but in order to prove lower bound, a classical method is like true hypothesis method. If you never heard about it before, just forget what I'm saying. But basically, you need to say that true laws are closed. And this is a bit tricky because even if you know that the law of the two original data set X are closed, it's difficult to say that also Z are going to be closed. Why? Because the fact that the two Z are closed will depend on two things. First one, as I said already like 3 times, on how much the two original data sets were closed. Second thing, it depends also on how much you can see. So it depends also on alpha, because actually, if you cannot see anything, you don't care about the fact that the two data sets were closed or not. It means that you're going to like create all the new public versions that are all the same. So the law will be closed as well. So let's try to see if there is a bit of literature on this context already in the case where you have just LDP, local differential privacy without the componentwise. And actually there is something. The very first paper was this one by Dwork, Rothblum, and Vadan. I'm talking about M and M tilde as the law of the public version. They are the law of Z tilde. And I want to say that if X and X tilde were closed, also M and M tilde are closed. And that's the reason why the first result from 2010 actually was not enough. This one was good in the sense that it made us understand the fact that alpha, so how much privacy we are given to the system, is really important. In the sense that if alpha is equal to 0, well, you are saying that the difference here is just 0, because makes sense. You are not seeing anything. Alpha equal to 0 is perfect privacy. So you are constructing all the sample in the very same way. And so they have the same law. But this was not enough, even in the case of classical LDP, to prove some lower bound. One of the most important results for statistical inference under LDP is the one published in JASA here from Ducci, Jordan, and Wainwright in 2018, where they proved exactly what I was talking about before, which is the fact that, yes, how much the two laws are close depends on alpha, so that if you give again alpha equal to 0, perfect privacy, you don't see anything, but also it depends on how much the original sample was close. So that if you give not a lot of privacy, but on the other side, they were close at the beginning, they're going to be close again. And that's nice. That's exactly the result that we would like to prove as well. But we have to be a bit careful because for us, not all the components have the same weight. So the law of the
So,
different, yes.
a quick question. So when you say classical LDP, you just mean that to each component we apply like an alpha LDP mechanism, essentially.
To all the component the same. It's not exactly the same as like applying to each component the same alpha. If you apply CLDP to each component, okay, with a different alpha j, basically you can prove that you obtain an LDP of level the sum of the alpha j.
Yeah, that makes sense. Yeah.
Okay. Uh, but it's not exactly the other way around because it's like you are considering a subset of all the LDP, and the subset of all the LDP are only the one for which you are like factorizing. If you think about the definition is given considering A, that is an element of the sigma algebra, and we are considering an element of the sigma algebra in one component, while the LDP consider the sigma algebra like in all the components directly. So
Okay.
if you
Makes sense.
basically, if you are considering the rectangular, then you go back to our case. But otherwise, it's not always the case. You can consider more general classes with LDP.
Okay, so when you say classical LDP, you mean using like an LDP mechanism that transforms like the D dimensions directly and
Exactly.
privatize it versus in your case, you're doing it
Exactly.
component-wise, so you have control. Okay, yeah, that makes sense. Okay, cool.
Exactly.
Thank you so much.
Thank you. Thank you. It's nice. I like the fact we're talking. So, okay, perfect. Yes, that's exactly the case. So here, the old vector has been privatized in the new vector. So with a certain level of privacy alpha, and this is the most important result, and we would like to find something like that. But as in our case, different components are going to have a different weight, are going to behave in a different way, we can already expect that for us, the marginals of the laws are going to play a role. And this is exactly what happens in here. I know that this is like, I would say, our main result. And I know that it's not super easy to be read. And that's the reason why I also wrote what happens in dimension 2, when we have a vector that has only two components. And in this case, what happens is that basically you have like the part where that involves alpha 1 that multiplies only the marginal with respect to the first component. So it means that how much privacy you are given to the first component, that is alpha 1, matters only if you look at the marginals on how much the marginals differ. Same things about alpha 2. So you are given to the second component a certain amount of privacy, alpha 2, and then you look on how much these two marginals are different. But then you have also this guy, when you look at the total law, okay, and think about the fact that all the marginals are actually smaller than the total law. So when you have the total law, you have something that is in general bigger, okay? But this is multiplied by something that is the product of this object. And the case of real privacy, so high privacy, is for alpha smaller than 1. So this quantity are actually small. And the fact that we are adding factors, it means that the bounds that we are getting are smaller and smaller. So basically, this quantity multiplying the largest object is the smallest one. And that's basically a way of already giving an intuition about the fact that this is sharp. The fact that this is sharp is also proved by the fact that you can use it for a lot of different applications. And that is what is really nice. Because you can take your favorite problem, you take like NIID random variables, right? And starting from there are a lot of statistical problems you can consider in the paper. We considered, for example, the estimation of the joint moment, the estimation of the density, and me, I'm so much a density estimation girl myself. So here I'm going to present what happens for the estimation of the density. And in this way, we can understand a bit better what's happening there. But what I wanted to say is also that you can choose your favorite statistical problem and you can see how much it changes if instead of looking at the data directly, you can look at an CLDP version of it after the privacy constraint. So let's say that now we want to consider the non-parametric estimation of the density of a vector, okay? We have this NIID copies of X, and we assume, as it is quite classical in non-parametric estimation, we want to estimate the density, and we assume that it belongs to a some older class.
Hey, I have a tiny
You raise
question.
that. Yes.
It's like I think I'm in school, like a raised hand. Yeah, just one question. Just not purely for generality, I guess. So in the last slide, yeah, I guess how much would things change if you used a different divergence? For example, I know like Behnush and Kharad, who are both in the audience, they usually study this like E gamma divergence, some connections to privacy, which they could probably say better than me. But yeah, like how much that change?
Yeah, that's a very good question. Actually, we started with the KL diversions like this just because it was natural.
Yeah.
And in the paper later on, also we extended to the case where we consider the DL divergence as well and the F divergence. But it's just less natural, I would say,
Okay.
because when you see really like this object appearing, you see very much that really like the right hand side, then you see the total variation appearing and so on. Then you can try to look at some other equivalents in some other distances. The constant changes, but not how they depend on the on alpha nor on the distance among the original data set.
Yeah.
So everything is good.
Cool.
Don't think that the constant is optimal too, but we really don't care about the constant, right? That's how it is.
Cool.
But that's a good point, yes. Thanks. Okay, so let's go on and estimate. Let's estimate this invariant density. Let's estimate the density in a non-parametric way. So we want to assume something, and we assume that it has a certain regularity that we call beta. Okay, and we want to estimate it under alpha CLDP. What does it mean? That first of all, we have to propose a concrete privacy mechanism to move from the X to the Z. Then we have to propose an estimator based on the Z. We want to see how fast, well, what's the convergence rate with this estimator and this privacy mechanism. And then it would be nice to say, yeah, it's the best one. It's not possible to do better. Okay. Otherwise, I wouldn't be here giving this talk. So this is going to happen. Let's start by saying that, well, if you want to estimate the density, there are a lot of ways, but as I was saying, I'm a density estimator girl myself, and I really like the kernel function. So without any type of privacy constraint, what I would use is simply the kernel estimator. But here, first of all, I have to be able to hide somehow the data. Okay, I have to be able to propose um, a mechanism to privatize them. How can I do that? Well, the idea in local differential privacy, and at least for what I've seen, it's more or less always the same. You add a nice Laplace and everything works fine. And that's exactly what we are going to do. Then the matrix is also about like understanding what's the scale parameter in the Laplace. But here, we are going to even see the proof together for how easy that is. We are going to see that together. We want to show that the Zij are alpha j view of the original Xij. So basically what we want to prove is that this object I'm just taking already the density of the privacy mechanism I explained before, is smaller by the exponential of alpha j. And in order to do that, we need to know what's the density of a Laplace. The density of a Laplace is this one. But we have decided to set the scale parameter really in order to get later on here the exponential of alpha j. And we can see that together in really like what's happening. Okay. In really just like one line. The density of the Laplace is this one. I just replace the parameter lambda with the parameter that we put here. And then if we look at this ratio, well, I'm putting the very same quantity here with x and here with x prime, okay? And the nice thing is that I can use reverse triangular inequality. So actually this z is the same and I just get that the difference is smaller than this quantity. But I have a nice kernel function whose infinity norm is bounded, so I can bound both of them with just 2 times the infinity norm of k that simplifies here, and we're going to get exactly the exponential of alpha j. So this is just a nice trick to say that each time that you want to create CLDP mechanism, adding a Laplace works just fine. So this is what we do, and then we have to define also what's the estimator that we want to consider, right? But in the case without any type of privacy constraint, one would use directly, I don't know how familiar you are, but without the extra Laplace, this is the estimator that you would use. And now what we do is to use instead the Z, so we are adding an extra noise. Is this extra noise going to play a role? Well, actually, yes, because here the dependence on alpha j make appear in this convergence rate, well, this rate in the end, okay? So we are studying the mean squared error for the estimation of the density, and we see that it depends on how big alpha is, okay? The first thing that I want you to remark is the fact that if we have perfect privacy, even just in one component, so it means that if even one alpha is equal to 0, one alpha j, it explodes. We lost it all. That's like, I would say, the main problem, the main issue, and the main thing that I would like to extend in the future. Because here it's not possible to give privacy to only some component or to give perfect privacy to one of them. Not possible. Alpha between 0 and 1. Okay. But then we can get this rate, and the question is, well, is it possible to do better? I would like to say that if you fix the level alpha 1, alpha d of privacy for the different component, you cannot go faster than this. This is the convergence rate we find, and that's the best one. Can we say it's optimal? Well, actually, yes. And the proof, it's really much based on the contraction of the Kullback divergence I was talking about before. Other than the contraction, this lower bound is really quite silly. It's quite easy, but the main part, the difficult part is to prove the contraction. And then what we get here is actually something that it's really like the same rate as before up to a constant if we say that alpha j is in the neighborhood of, well, it's smaller than 1. It's in the neighborhood of 0. Because in this case, this is just alpha j, so I can go up. This was the rate before, while now the rate is this one. So it's really the same up to say that this behaves as alpha j. We are happy because it means that if someone else arrives and tell us, hey, I think that this other privacy mechanism is better than yours, and still the privacy that it ensures is exactly the same as alpha, I can tell you, well, in which sense? At least not in a minimax sense. In a minimax sense, it cannot be better than ours. Everything is good with ours, okay? And then there are some other possible application. As I was saying before, you can take like your favorite statistical problem and you can apply CLDP and see how much it changes. But there is something new that it was not possible to consider in the case without privacy. That is the problem of the effective privacy. And it is basically the last thing that I want to talk about before I say hello to you guys. And this is the first problem we started with, which is the fact that, as we were saying before, the component may be dependent among them, right? So let's say that I'm really interested in understanding how much I can see of X1. X1 was the salary in our previous example, okay? And I want to cover the salary. So what can I see? I see not only Z1 in concrete, in the reality, I not only see Z1, which is the public version of the salary, but I also see Z2, Z3, Z until ZD, that are the public version of how much I'm spending for shoes, bags, boots, nails, dinners, and even like better things, let's say, okay? And I want to say how much they are revealing about my original salary, okay? So I want to understand how much information they are carry about the original value x1. X1 is the one that we really want to hide, and x2, xd are all the other things that are maybe dependent with respect to x1, maybe not, but they for sure give some information about it in z2, zd. And what we can see already is that, well, how much my privacy guarantees are worth really depends on how much they are dependent. So how much extra information they are carrying about X1. Because if they are completely independent, well, even if I can see also Z1, Z2, Z3 until ZD, I'm not recovering extra information, right? They are independent, there's nothing there. So we need to introduce a way of quantifying the dependence. And our idea is to introduce this delta ind that basically is telling us how much all the other components from x2 to xd see the fact that x1 changed. Okay, so I try to consider what happens when x1 is equal to something or to something else, and can I see the difference in all the other components? It's nice the fact that this quantity is between 0 and 2 and is exactly equal to 0 when x1 is independent from all the others, and in the like opposite case where I take, for example, all the components to be exactly x1, this is equal to 2. Okay? And the result about effective privacy is the following. Remember that the privacy parameter equal to 0 means perfect privacy. And then if it is bigger, it means that we have less privacy, okay? So here, what we are saying is that if we see only the component Z1 that has been constructed starting from X1, the privacy that we are giving is alpha 1. But if instead of looking only the first component that was associated to the salary, so instead of looking only the public version of the salary, we look at the public version of all the others, we get some extra information. How much? Where we lose in the parameter because we get a new alpha, if you want, that is alpha 1 plus something else. And that something else really depends on how much dependency there is. So remember, if all the other components were independent from x1, this delta ind was equal to 0. So if they are all independent, this second part is just 0, and the effective privacy is again just alpha 1. But in the other scenario, where actually the components are dependent, well, we are losing something more, and that much depends on how much they are dependent and how much privacy we are giving to the other's component. And that means that there is a leakage of privacy, which in general is something that finally it's quite negative. But remember that sometimes that's how it is. There's not much we can do. If we receive data from different companies and they already gave us things with different alpha level, that's life. That's life, and we need to be able to say something. So just to wrap up, the take-home message, what have we done? We have formulated the CLDP, and we have seen more or less what happens when we consider this component-wise formulation instead of a formulation where you just put the vector and you give privacy to the whole vector. And we have defined the minimax risk in this case. in order to understand what is an optimal privacy mechanism under component-wise local differential privacy, we needed to prove this contraction. And once we have proven the contraction, we were able to understand the fact that if the original data were closed, then also the other data were closed, which was basically the main point. It was crucial in order to prove optimal result in a lot of different applications that can go from density, mean, covariance estimation. This is really like super versatile if you want. And to conclude, we have seen privacy level. There are other applications. I mean, if you want, we can discuss it later. But that is all. I wanted to thank you for everything, and that's it.
Thanks very much.
Thank you.
So I have maybe one or two questions, but does anyone in the audience have questions? Okay, just in case. Yeah, so I just had like a kind of really like general question, something I guess that I was wondering about this summer, and I guess it's related to this. So yes, yeah. So I guess when you're thinking about component-wise privacy or like just like privacy in general, like you often like use how do you say? I think it's on page 18, for example. And my words are
18.
not in the morning. My words are not like there yet. So
Don't worry. You said 18 or 8?
maybe sorry, maybe 16. Sure. Yeah.
16.
I think this is what I wanted. Oh no, okay, that's okay. So I have some really hard to decode notes. Sorry, actually, let me ask a question
Don't worry about it.
about page 16. So I had a different question, which now I understand what this number 16 means on my paper. Yeah, so I guess so this is like sort of general RD value like valued like random vectors, in some sense, right? I was wondering, for example, can the rates be improved if you knew, for example, that the support of like their law is somehow low dimensional, like it's finite, like it's like finitely supported or something like this, or like on some low dimensional manifold or something like this,
Uh,
especially finitely supported, I'm thinking, because you could always embed things into
okay.
the real line.
Okay. Yeah, actually, in this part, in the when we consider another application, which is, for example, the mean estimation, we do use the fact that, for example, we're using the fact that the law is supported on a compact and so on. We otherwise, just because we want to consider a very easy example,
Yeah.
and in that case, otherwise, the rate would have been worse and so on. So in that case, knowing that the law is supported on a compact helps very much. In this case, I don't think it would help very much just because finally, like with the kernel function, we are anyway shrinking everything like
Mhm.
in the neighborhood of a certain x. And so finally, everything is pointwise. So I don't think it would help much. But on the other side, like knowing really something more about the law, like considering some different data, maybe it would help somehow. Like if you can use some other maybe different approach than kernel density estimator that are a bit fancier, maybe you could do something more. I don't know.
Cool. Cool. And actually, I had like one more question, but now I remember how to formulate it. Um, yeah, sorry. I only had like
No, don't worry.
um,
See, that helps.
sometimes. Um, yeah. So like, I guess one thing I was wondering is that when you look at component-wise, so actually this relates to something we're talking about the summer with Behnush, for example. So if you consider component-wise privacy, or like something we also thought about a bit, um, I guess one question is that how do you say, maybe sometimes you'd only want like some information about a component or some set of components. Like, I mean, like a moment, so maybe some measurable function, not necessarily like the projection function, which is the component-wise privacy. Do people ever study this? So for example, an equivalent way of what I'm trying to say is that like the TV distance is an indicator over all measurable sets, but maybe you only care about some subset of test functions, because maybe you don't care about all this information. Like, do people think about this, or how
That's
do you solve it?
that's a very, very good point. That's a super question. Okay, I have I have a lot of things to say about that. First of all, it's very interesting also because to care about only like a subset of the things that you have. Also because when you are in really high dimension,
Yeah.
privacy doesn't work well with sparsity. So it means that even if like in the classical high dimensional set, you are able like to push the convergence rate to be independent just of the parameter of sparsity instead of the dimension.
Yeah.
In the case where you apply privacy to the whole vector, this paper that was like the one that I talked about as landmark before, this one also shows that privacy doesn't work well. And so, And so actually it would be interesting, I think, to push exactly this, the component-wise local differential privacy to the case where you can observe only a subset, because in that case, maybe you would be able to recover something that depends really on the sparsity rather
Yeah.
than on the dimension, because you give privacy only to a certain component, to a certain number of subcomponents. To be honest, I haven't seen much. I think that people worked also on it from the point of view of, well, it's connected to fairness as well. Because if you think about it, like maybe you have again a vector that is the whole person and you have a lot of information about the person, but like a couple of components are, for example, I don't know, the gender, the race, or something like that, and you want to hide only those components, maybe the others are maybe public. And well, there are a lot of things on fairness, but not really connected to component-wise local differential privacy. But that's another reason why I was really saying that what I would like to do is to extend this paper to the case where some alpha may be equal to infinity. That means basically that you are
Okay.
giving like you are giving privacy only to a subset. And actually, I think that if you consider the upper bounds in the application that I talked about right now, you just need to be a bit more careful, but everything seems to work fine. The
Cool.
bad thing is that you need to be able to extend this to the case where only some components are actually privatized, which means that basically here it's not clear exactly what you should see in the case where alpha goes to infinity. Because if you just look at this bound, in the case where even only one alpha can go to infinity, this is completely uninformative
Yeah.
because it says that it's smaller than infinity, right? So it should be reworked. And I think that there is hope. I think that it would be super nice, but so far it's not there. But I think it's doable.
Yeah, I think so too, right? I mean, I have no idea, but if you say so, I think I believe you.
Yeah,
Maybe one last question, just purely
yeah,
curiosity.
yeah, go.
Um, yeah, so yeah, so it's okay. Like I know, well, like I've heard in some settings, like in more classical, like LDP, in the finite state space example, like there like how to say optimal privatization mechanisms are known, like the ones that realize the min-max bound, you know. But I mean, like the version of the max bound. But is there any like yeah, is there any such thing here, like a mechanism that actually realizes it explicitly?
That's another very good point. Actually, here it's easier because it's optimal in a different sense.
Hmm.
Because here it's optimal in a minimax sense, which is actually easier. Like for example, the mechanism that we prove, like that we use, even the just Laplace one, is
Yeah.
optimal in a
Oh,
minimax
really?
sense.
Oh, okay. Sorry. Yeah, yeah.
So
Yeah.
that one is easy. Well, I have to say that alpha j is small enough, but the optimality that we're talking
Right.
about, like in
Yeah.
the case where we are, for example, in a finite alphabet and so on, are more complicated to be achieved because it's more optimal. Like I think that if the paper are the same we're talking about, it's optimal like from an efficient point of view, and that is way more tricky. And for example, there are a lot of things about the fact that, for example, the staircase mechanism seems to be optimal under like this efficient point of view. There is one very, very nice paper from Lucas Steinberger talking about it also, well, talking about it for the Fisher information for the estimation of a parameter on the
Mhm.
still on the annals. There are a lot of there are a lot of nice results, but I think it's a way trickier.
Okay. Interesting.
It's a way trickier optimality.
Cool. So
It's pretty difficult because it involves like a maximization problem
yeah,
on
yeah,
space that are not convex. So it's yeah, it's more functional analysis point of view than this one that is more a statistical point of view, I would
yeah.
say.
That makes sense. That makes sense actually. Yeah, pretty cool,
Yeah.
actually, to be honest. Oh, wait, let me
Uh,
stop the recording.